Thank you so much for providing me the opportunity to talk. My name is Peter Swart. Unfortunately, I can't be there. I think it's an amazing meeting. 12 time zones, I think 12 and a half time zones ahead of you guys, so I have not been able to see everything. Today I'll be talking about covered affairs. It's very much towards multimodal data fusion with confidence, as you will see. I think this is a slide that doesn't need to be said, but I'm going to do it anyway. Combining different experimental modalities provides very unique insights and materials not otherwise accessible. You can use different things like mass spec, infrared spectroscopy, or X-ray methods, or electron methods to look at different aspects of your material and get really unique views. Now, different modalities provide very different insights, and the final utility, what you want to do, actually determines how you treat the problem of data fusion. For instance, the stuff that you need to do with the data, if you just want to use one modality to speed up one experiment, is completely different if you want to do something else. So, for instance, in the ALS, we are using infrared to find out where to do interesting mass spec imaging stuff. This is an air lab technique pioneered by Hoying Holman and BSISB. I will not be talking about that today. I will be talking about a different kind of analysis, and that is when we want to estimate joint modes. How do we stick together different kind of observations in space and see if we can estimate the joint modes. If we can basically say, hey, this voxel has this X-ray density and this spectral property. That's roughly the idea here. Combining insights from multiple modalities is most easily done when you can just fuse the data together. This is the joint mode thing that you can do. Well, how can you combine experiments? The easiest way to say, okay, we do this in hardware. There are very great opportunities to derive or to build new instrumentation that actually allows you to do measurements on the same sample in the same location at the same time. This is not always possible, and then you start to look at computational approach in order to merge things. And there's a lot of prior art. For instance, in remote sensing, data fusion is very normal, as well as medical imaging. How does this typically work? Typically, what you do is you establish some sort of mapping from each modality to a common semantic framework. For instance, you can use SIFT or RIFT or deep learning based methods that basically say this modality with these features maps to this kind of thing, and then I have another modality, I see the same kind of thing, like an edge, a corner, and once you map those different modalities, so to that kind of framework, you can then use a geometrical alignment. You can perform a geometrical alignment using just simple rotations and translations and image warping as well in order to take care of things. And then after that, you have to concatenate the data. Sounds easy enough. It isn't, because samples actually change. Yeah, you can have stuff moving. Beam damage is one thing, but Odetta was showing earlier this morning stuff with her SEM EDX. You take a sample and you actually cut it up. Pieces can fall off. You can lose coordinate references. Yeah, you don't know exactly where you are sometimes between different observations. Different methods can also have different resolutions, right? And that makes life hard as well. The X-ray tomography stuff that we'll be talking about today has a completely different resolution than the SEM EDX stuff that Odetta was talking about earlier today. There can be a dimension mismatch as well, which makes things tricky. Some data is three-dimensional, other data is two-dimensional. Practical issues. Data can be very large. That's a problem. That's a challenge, something to take care of. It's not trivial. And my favorite thing is you also want to know how well you're doing. So you need some uncertainty estimates of A, the input, and B, definitely the output. How did I get into this into this project? Well, this is something that actually was put before the camera team by Odetta and Tomas. They trying to understand soil. It's a crucial part of our ecosystem. We want to understand it in all aspects. Structurally, if you want to know grain and pore sizes, connected components, and things like that, you can use X-ray tomography. If you want to understand it chemically, you want to know elemental and mineral distributions, you can use scanning electron microscopy with the energy dispersive X-ray analysis. It's a spectral imaging tool, SEM EDX. How do you, the question put in front of us, how can we combine these modalities to basically get an SEM EDX map on three-dimensional data from XCT? So XCT is fast. It's three-dimensional, medium resolution. It's just single channel though. SEM EDX is slow-ish. It's 2D. It's very high resolution. And it's multi-channel. So it would be extremely nice if we can take our three-dimensional XCT map and then somehow in-paint it with realistic SEM EDX data. Yeah, that's roughly what we're trying to do. If you go back to the basic workflow that I outlined, how these things are typically done, we've implemented something like this with a tiny twist. Basically, the way that we try to attack this problem is that we take our SEM EDX data and we build a neural network that translates this data into a surrogate XTC model. And that surrogate XTC model is then subjected to loss in resolution and image warping so that we can match it to the data. Once we have that surrogate model in place, we can actually invert that surrogate model right here. So here you go from SEM EDX data to pseudo XTC data, and we make sure that it looks like real XTC data by matching it up with the XTC data that we have. And then once we're capable of having the surrogate model right here, what we actually do is actually train a new model that actually takes it backwards. So first we make sure that we go forward, and once that's done, we make sure we can go backward. And once we can go backward, we can basically take any XCC data and then pass it through, and then get pseudo SEM EDX data. So there's some issues, some geometrical alignments. Might have warped cut planes, or we might not know exactly where we cut things, and some pieces are lost or stuff. It's not easy. We're getting somewhere, which is good. Well, we call it a good first pass, but it has a number of drawbacks. One of the things that we're doing right now, and you can probably see that here, is that we treat the data as a 2D system while we actually have three-dimensional information, and you can actually potentially lose information. So if you look here at this cylinder, if you look at it from one angle, it looks like a rectangle. If you look at it from another angle, it is a circle. It's a disc. If you don't have a lot of information, and if morphology is important, this can actually really drive your analysis. The other issue is that we get a single answer, but single answers are not very satisfactory, because we really want to know how certain we are of our prediction. And trying to illustrate this here with a fictitious stock, that we have a model that basically says that the performance over time is going to look like this. And you say, oh, this is great. The thing is going up over time. This is a great investment opportunity. The issue though is that the predicted median of the performance over time, it doesn't really say much. We have no clue how accurate this prediction is. So if we can actually paste in a prediction interval, a 90% prediction interval, basically says in 90% of the cases we think that the performance of this stock is going to look like this, you actually see that there still is a decent chance that you're actually going to lose money. So, but there's also a decent chance that you're not going to lose money, right? So, depending on your risk tolerance, you actually say, okay, this is something worth doing or not. If your risk envelope, if your prediction interval looks like this, then and if you don't like making money, this is a great bet, right? Because in 90% of the cases, it's very likely that you come out ahead. So a point estimate alone can be very misleading, and if you have an uncertainty estimate associated with a prediction, it can really impact your decision making. And we of course want to use the observations that we have for decision making either something practical or something scientific in terms of what's happening. So that's what we're trying to accomplish here. So how do we do uncertainty quantification? The couple of approaches. You have the very classic stuff based on the second derivative of the logarithm of some sort of likelihood function. It's very classic stuff. It's the basic method for most least square kind of approaches. There's Gaussian process regression. Fantastic stuff. Basically, it says that any kind of the uncertainty of any prediction is associated to all the other points that you have based on some kind of covariance model that you attach to it. It's very nice, has some drawbacks. I'm not going to talk about that. Other method is an ensemble method. So instead of training a single model, you can train many. The mean prediction is typically better than a single prediction, and the variety in predictions is probing how certain you are to prediction. And there is something called quantile regression. And quantile regression is a method that uses a specific loss function that estimates the quantiles that you're interested in of your prediction. And that's a very powerful and very useful method. Now I'm going to do something that I can only do because I'm remotely. I'm going to say something wild. None of this actually works. Like if I'm actually physically in the room, I'm scared that the Gaussian process regression will physically attack me. So that's why it's good that I'm on the other side of the world. It works. It's actually in quotes. Of course, this is not really fair. So what I actually mean by this is that unless you meet all of the assumptions of your method, you actually don't have a guarantee that the produced predictions in terms of the uncertainty the uncertainties that you get, they're actually correct. Like in Gaussian process regression or the Fisher information based approaches, there's a lot of stuff that actually has to be met before that is actually correct. So if you actually want to make sure that it's correct, you actually need an additional calibration step. And that calibration step is actually fairly straightforward, and it's a technique called conformal prediction. So what we are actually going to use here is not Gaussian process regression, because our data sets are too large for that to be possible. What we're using is conformalized quantile regression via ensembles of random neural networks. And I'll show you exactly how that works right here. So the idea is to train an ensemble of neural networks that map some high noise data to a medium noise data. So what we're trying to do is we're basically trying to build a relationship, a function that takes this high noise data set here to say the ground truth right there. What we're going to do is we're going to build a neural network that actually is a random neural network. We need random neural networks in order to create a great diversity in different models so that we can use these ensemble methods. The random neural networks that we have, they actually have an interesting property. In goes one channel, out comes 8 channels, and then we just stack 3 different projector heads to this. We do this a couple of times. Actually, we train n times typically. I like odd numbers, 5, 7, stuff like that. Although I've been known to use 12. We then get a simple average, and we use quantile regression, like I said before, to get lower quantiles, median, and upper quantile. And then associated with this is a conformal prediction step, which is really, it's like 3-4 lines of code that subsequently calibrates out the quantiles that you get. This is done using Dilcia. You can Google Dilcia, and then you get to the web page or the paper or the code, whatever your search history says you like. And it's, of course, pip installable. Here's an example. Here we have a noisy image. This is the ground truth image. If we have 64 independent data frames, you can basically see what's happening right here, that the median score, the mean score, the score of the mean prediction actually in an ensemble setting actually is a lot better than the individual ones. That's really the power of these ensemble methods, that it allows you to leverage different kind of models to get better. What about the uncertainty? The uncertainty, so the quantiles you see right here. Here you see the same image. I uncapped the dynamic range of the image so that you can see the full range. And what you see is that the uncertainty estimates that we get on the predictions look really decent. We asked for a 90% coverage. What does that mean? 90% coverage means that in 90% of the cases, the ground truth value actually lies within the interval that we estimate. And of course, 10% of the cases it doesn't. And you see that 10% of the cases highlighted here in green. I think this in this particular slide is like 11%, but it's not far off. It's well within the margin of what you expect it to be. Another thing to look at is that the error estimates that we get, they are adaptive. What does that mean? In some areas the errors are small, and in other areas the errors are big. And that's what it means, and that's what you actually want. Otherwise, you can just slap on a number and calibrate it out. That's not very informative. So that's how we do error estimation. Moving on to, I mean, this is a 64 by 64, maybe 128 by 128. I forgot exactly how big it is. It's not much of a challenge. X-ray tomography data typically is in the order of 2K by 2K by 2K. I think I'm butchering the numbers a bit. It might be 1700 by 25 by 25. It really depends on the system that you're running. Odetta was talking about her EDX large area measurements. I suspect that those images are going to be humongous as well. Nevertheless, 2K by 2K by 2K density from tomography is 32 gigabytes. My RTX 3090 is 24 gigabytes. So the data plus any kind of neural network that I have on there doesn't fit on my card. So you need to do something, and that something is Quilty. It's a procedure that basically allows you to take a large tensor and chop it up into smaller chunks. That then allows you to train on smaller stuff. And then when you want to do inference, you can actually go back. And you can basically have this cube marching throughout your 3D volume or 2D thing, and you can iterate over things, and we don't lose positional information, and we use the disk as a cache, so you can stitch things back together. And it is done in such a way that you can have overlapping or non-overlapping boxes or squares or rectangles, whatever you fancy, and make things work. This is a segmentation example. Not going to go into it because it's not really relevant to this talk. But as you can see, you basically take a large data set and you chop it off into smaller pieces, and then you can handle it. So let's do something real. This is an SEM EDX data set that I got from Odetta. I have 3 data sets after chopping things off of areas that just didn't look good. I'm having something of the size about 750 by 1024. I have three types of measurements. I have a 7-second exposure, which is what you see right here. This is a 3-channel image with aluminum, silicon, and iron. I think you guys have a very hard time seeing what's going on here. There's a reason for that, because this data is super noisy. There's some red and some green, and you might be able to see the blue. If we actually go to 70 seconds, it might actually become a little bit more clear what's going on. You do start to see the iron here, and silicon and aluminum becomes a lot more obvious. And this is what you get when you go from 70 to a little bit over 7,000 seconds. And that's how your data looks. So the question is, can we actually take this image and can we turn it into that image, or can we take this image and turn it into that image? This might actually be very interesting for the large area measurements, right? I mean, if you want to get a super quick scan of a very large area and get a half decent prediction of how this looks, you might actually be able to change your measurement strategies and speed things up tremendously.
Peter,
what do
can
we
you
do?
wrap it up quickly?
Absolutely. So what we can do is we can pass this through the pipeline that we have, and what you can see right here is that when we have 7 seconds, we get great answers. We have good confidence intervals, and we can extend this trick to three-dimensional data as well. Using exactly the same approach, we can take a high noise tomography data set and map it to a medium or low noise data set and get a decent prediction out. These are the confidence intervals that we get when we run this. So the aim of this work is to perform multimodal dataset fusion while still yielding results that provide us with estimates of some uncertainty metric of our predictions. We can do this. This can be done in other scenarios as well. And we are developing the tools to tackle sub-problems that have some standalone utility, like uncertainty quantification, big data stuff, as well as handling dimensional resolution mismatches. So at present, we are building these general tools that can be used across different scenarios. Quilty and DLC are already extensively used for segmentation in synchronous light source applications, and they are embedded in larger pipelines. And ultimately, we really want to provide a set of tools to construct pipelines for data fusion that can be embedded in other pipelines or be used for something else completely altogether. Our code is open source and it is documented and tested as much as we can stand. I'd like to thank a couple of people, of course, James Sethian and Eric Roberts, who have been instrumental in this, as well as Thomas and Odetta for their support, data, and ideas. Money comes from LDIDs, various DOE flavors, and NIH. And you can Google these things, or you can send me an email. Thank you.